Welcome to day 7. So our goals for today, we're actually going to do something different. I know you're like, oh, take a little bit of a break. This is, okay, I'm dweeby. We all know that. But I enjoy sampling. You're like, what? Let's go back first of all and recall the advantage red example. Remember the research question, which was in a sports competition, is there an advantage to wearing a red uniform rather than a blue? And we found the p-value to be pretty small. It was about 0.04, and that's provided us strong evidence that red uniforms tend to win over blue a majority of the time. But to what kind of sports events do these findings apply? And we talked about that a bit, saying, well, what can we do? Can we apply the findings to non-Olympic events, other individual sports, team sports? Remember, this is one of those things that we want to not forget. We want to keep in mind as we move along. The objective in statistical investigations is to use data from a sample to infer about some large population or process. So hopefully we find some information that we can then generalize. All right. Here's some keys though. We can generalize any findings from a sample to only a population or process that the sample is, and here's the key word, representative of. Whoops, and I already. All right, there, that's spelled correctly. So we can generalize findings from the sample to population or process consisting of observational units like those in the sample. So we have to be careful. We could, when we were looking at our advantage red example, we know that these were combat individual sports. So it doesn't make sense to draw it to team sports. Other individual sports, well, probably not. Like tennis, not necessarily. They're very different. So some terminology that we want to make sure we understand is a sampling method is said to be biased. Now, biased is generally, when you think about something being biased, it leans towards something. Is that necessarily good? Well, we don't want a biased sample. We want it to represent the population that we're pulling from overall. So a sampling method is said to be biased if the sample statistics from samples drawn using the method, whatever method it is, how we're sampling consistently over or underestimates the parameter of interest. All right, so we want to make sure that we have an unbiased sample. Okay, so what we want is unbiased. So let's look at an example. Example 1 here. Which of the following has a better chance of giving you an unbiased representative sample of students from the Cal Poly student population? The key here is, what is our population of interest? Well, our population of interest is the Cal Poly student population. Okay, students from the Cal Poly student population. So we know we really want to see a little bit about all of the students, right? Or we want to look at a representative sample of all Cal Poly students. So let's look at these different ways and see which one would give us the best sample so that we could draw conclusions. How about first one, a random sample of 100 students in the library on a Thursday night? What do you think? I'd say no. I think that's going to overrepresent students who use the library on Thursday nights. So the first one, no. It's going to exclude those students who are working off campus or are going to farmers market, don't have Friday classes, let's be honest. So yeah, that's not a great one. How about a sample of 100 students in the student center on a Friday night? Well, once again, it's looking at students who use the student center. What about all the students who don't? Not a good choice. A random sample of 100 students at a basketball game on a Tuesday night. Well, that's assuming that they have an interest in basketball. Is that representative of all the students? No. Some students don't like basketball. They wouldn't go to a game. How about a random sample of 10 students from 10 randomly chosen dorms on campus? Ooh, this one's starting to sound better. But let's think about it. We know that they guarantee housing for freshmen, and this is a special year with COVID, but in general, are there a lot of students who live off campus? Yes. So, no, not a good one. How about a random sample of 100 students from cars registered on campus? Well, yeah, a lot of students don't have cars on campus, so no. How about a random sample of 100 students from the registrar's student list? Do you think the registrar has the most complete student list? Most definitely. So this is going to give us a complete list of all students including all of those in the ones above, in those example options 1 through 5 above. I suggest pausing for a moment. You're going to notice this showed up on your screen, and write that down. One thing to keep in mind is you always hear about random sample, random sample, random sample. And you automatically think, oh, that's, at least I do, that's a good sample. Well, just being a random sample does not make a sample representative of the population of interest. All right, so just because it's random doesn't make it representative. Let's pretend that instead of looking at, we were interested in all Cal Poly students, how about we were interested in sampling all Cal Poly alumni? All right, so if we look at all of these options 1 through 5, well, obviously they don't make sense. And 6, well, the registrar's student list. But that's the registrar's current student list. You'd have to specifically go to the alumni office and have them give you a list, all right? Making a sample bigger, just saying, okay, if you're pulling from the wrong spot of any of these, let's say you're like, well, I'll pull 200 students from the library. Is that going to make it any better of a sample, random sample? No. Okay, so just increasing sample size is not going to fix an inherently bad sampling method. So there's a passage below, 7 years ago, our fathers. Anybody remember what that is? Anybody remember? Yes, Gettysburg Address. So we are going to take a look at this. Whoops, Gettysburg, write that twice. Gettysburg Address. We're going to do something called literacy computing. So we're going to work a little bit with literacy computing. It takes passages and studies them. It can be used to check. There's lots of things it can check. I don't want to belabor the point here, but it's looking at passages and doing some computations. So suppose that we want to characterize this passage by the average length of words. We consider this passage of 268 words, so we have 268 words, excuse me, and that's our population of interest. So we know if we draw words from within here, is that going to give us a sample from this passage? Yes. Okay, so because we're looking at the correct passage, we can draw words. Big note here. This is really an artificial situation because we already know the value of the parameter. Could we look at each one of these words, count the number of letters in each one, divide it by 268 words, and come up with a number, the parameter value? Certainly. So why am I doing this then if we already know that? I'll keep reading here. As we know the value of the parameter, we do not need statistics to estimate a value for the parameter. But why we're using this example is that so you can see how the values of statistics are related to the value of the parameter they're estimating and how to take a representative sample. So there is value in it, but remember, this is an artificial situation. So pause, see if you can fill in these next two by yourself. Hopefully you remember the observational unit. What we're looking at is each word. The variable is the length of each word. That's what we're interested, or the number of letters. Either one of those would be fine. And obviously it's quantitative because we're going to count and take averages. Now, say that you will have you will take a sample of 5 words, record the length of each word, and calculate the average of the sample. In this context, what is the parameter in the statistic? Think about that for a moment. Now we do have a bit of new terminology here, and I'm going to hit that first. A sample average is denoted by X bar, and that's what the X with the line on top means, X bar. And a population average is mu. So we have the sample average and the population average. So when I look at the parameter up here, I see that's going to be, we're going to look at mu, the population average, and that's mu is the average length of all 268 words in this context. And the statistic is X bar, which is the average length of 5 words. Now, I'd like you to all do this individually. I'll show you how to do it. But it's kind of fun. Okay, maybe it's fun because I'm a dweeb, but let's take a simple random sample of 5 words from the passage. We're going to do that by going to random.org to generate the IDs of 5 words of your sample. In random.org, we're going to set the minimum of 1 because we want minimum word being count, the first word, and the last word is number 268. We're going to click generate and record in the table below the ID of the first word and then generate 4 more times to get a total of 5 IDs. So I went to random.org and we see that there's the random number generator here on the right-hand side. One number is, we start with number 1. We have 268 words total. So I'm going to hit generate. And I'm going to record that on the spreadsheet. So that ID is 31. And remember, I'm asking to get the average of 5 words. So I need to generate another one, 135. What if I generated 135 again? I would just skip that. I would just click generate again. 259, 127, and finally 8. So I'd love you to take a moment, do that, put in your IDs, and then go and find the word, and I'll show you how to do that. So I wrote those down in the sheet so you can see it. Now, how would I find which word those go to? What I would do is I would scan up here, and this, just so you know, this is word number 1, word number 2, 3, 4, 5, 6. To make it easier, what they did is this first word here is word number 17. So the very first one I had was word number 31. So I know my first word is now. So if you're following along, go find your words and then come on back. So I went and found the word that associated with my number. Now, if we were in class, what we would do is I'd have everyone come up with options. How are ways that we could, instead of using a random number generator, how could we come up with words? Some people suggest, well, what about just, pointing at a word? Well, what do you think we're most likely when your finger lands, given area? Are you most likely to land on a long word or a small word? Probably on a long word. People come up with various methods, but random number generator is the way to go. As a CPA, I use that quite a bit. Now, we want to count the number of letters in each of these words and record them. Now, based on the table, what is the average length of the words in the sample? What we're going to do is take the 3 plus 5 plus 6 plus 4 plus 7 and divide by 5. So if you're doing it along with me, pause and get your average. That was lucky. For me, it came out to be exactly 5. Most of you will end up with a decimal. Is this X bar or mu? This is something that it's very important to make sure that you understand the difference. Hopefully you say right away it's X bar because it's a statistic. We did it based on the sample. Remember, mu is related to the parameter, that long run, looking at every possible, in this case, 268 words, average of all, X bar looks at just the sample. If we were to repeat that process, taking random numbers and writing down the words, counting the letters, we repeated that sampling process, would the sample average likely change or stay the same? Now, hopefully at this point in the quarter, you're ready to say the sample mean, sample average would change. All right, why? Because remember, there's going to be each sample, you're probably going to get different words, right? So there's sample to sample random chance variation, all right? The sample averages means would likely vary from sample to sample due to sampling variability. All samples aren't going to be identical. So it makes sense that it's going to change a little, they're going to change each time you take one. So how do you know how good our sample might be at representing the population? Same as we've done earlier. We can use simulation to see what happens when we know exactly what the population looks like and generate samples from the known population and track how the sample averages behave. Now, to explore the long run pattern of X bar, we're going to use the applets again. Before we go on to looking at samples some more, I want to look specifically at this graph right here. You notice the key word here, population data. So is this giving us all of the information about the entire population? Yes. Remember, this is an artificial situation. This population size, you notice, is 268 because there are 268 words in the Gettysburg Address. And I ask, what is the mean and standard deviation of the graph? Well, we know it tells us that the mean is 4.295 and the standard deviation is 2.119. Now, the big thing that I really want you to keep in mind here, so you know how to, you can see that right here. Are these parameters or statistics? Given that it's based on the population, these are parameters. So let's use the correct symbols to record these. So my population mean is mu, 4.295, that's given to us. And we're also going to use sigma, and that's going to give us our population standard deviation of 2.119. And we see that these pertain to the population because, well, it tells us here it's the population data. As you can see, I've moved away from the notes and I pulled up the Rossmann-Chance applets. Now, it says in the directions here that we're going to look at sampling words. So I'm going to click on that, and you should see here exactly what I have printed in your handout. This is showing the population, and you can tell it's population because it says population data. So we took one sample earlier by using that random.org and getting numbers, and now these applets have this great option that you can click there and it says show sampling options. And what we're going to do is we're going to leave the number of samples at 1 for right now, but our sample size, what have we been talking about? How many words? Well, we've been talking about 5 words. And then I'm going to click on draw samples. And it comes up and it gives us the words that it drew. Now, if the word is too long, we'll get something funky. It won't necessarily, the answer that the average it'll come out with will be a little bit strange. Once in a while, the app will have problems if there's a really long word that goes over to here, but you can see here's each of the word people with word length 6. It's word number 256, and it shows us here, if you add those up, that totals to 25 divided by 5. Oh, there's your sample length. Your sample average is 5. So I'm going to record that, and then we'll go back and I'll flip back in a moment. But let's say I want to take another sample. So I'm not going to hit reset. I'm just going to draw another sample. Sorry, I was trying to use my mouse there. That was the pause. So there's my next sample. This time, if I look at the words, I see we is in met this. are these randomly drawn samples? Yes. But what is our sample length this time? It is 2.6. And you, of course, can do this along with me as you're going through. Now you can see here we have the most recent sample, and then overall we've taken 2 samples. The mean is 3.8 between them, but we want to have a lot of samples, right? And this time I know to click instead of use my mouse. I want to get to 1,000, so I'm going to have to pull 998 more. And I'm going to draw those samples. Oops, sorry. Sample size is 5. I clicked in the wrong box here. The number of samples, excuse me, is 998. Sample size does not change. And I draw them, and then boom, I end up with a distribution. So the very last sample I drew happened, so number 1,000 happened to have an average of 4.6, average length, mean length. But overall, here is when I did, there's this 998. I must have accidentally hit reset. I apologize. Let's see here. Now we have a total of 1,000. Sorry about that. My mistake in the middle there got me, I should say. You guys are probably fine. So there's now, and you can always check yourself. And that's one of the sweet things is that you can check and see, oh, now I have a total of 1,000 samples right here. You see the 1,000, there's my mean, and there's my standard deviation. So doing this on an iPad, heads up, be careful where you're clicking exactly because you may get something you don't want. But the nice thing is that you notice when I tried to do a sample size of 998, it said, no go, you only can do between 1 and 268 because there's only 268 words in the entire population. So I recorded my 5 and then my 2.6. I said, in theory, I should have said it's 998 and then just hit draw samples and I'd have a total of 1,000. So I did this earlier, so it's a little bit different than the one that was before, which makes sense because remember, every time we draw a null distribution by drawing samples, it's going to look a little bit different. So we have a dot plot of sample averages on the bottom. And I have a screenshot of that here. If anyone's interested, I use snipping tool. It works really well. And this graph shows us the approximate distribution of the sample length of mean length, length of words from samples of 5 words. So how many dots should there be total? What would you think? Well, hopefully you're saying 1,000 because that's how many samples we drew. So hopefully you know too what each dot represents. It's the sample length of a randomly selected sample of 5 words. So this is what we've been doing again and again and again. What's the shape of the distribution? Well, I look at this and it looks like there's some funky stuff hanging out in the tails a bit. I'd say since there's more, it seems like the shape is, if I drew it, it's here, but then there's some stuff down here. All right. Obviously not going below there. As there's some things in this end of the tail in particular, I would not say it's fairly bell-shaped and I'd say it's slightly skewed, and I would slightly say slightly skewed to the right because the right hand is pulling up the average a little bit higher than like these observations up here are pulling that average up a little bit higher versus if those weren't there, those few. The next question asks for the mean and standard deviation. Obviously, we can see that that is reported right in chart there, and let's go and record that. Notice that I used X bar because remember this is using a statistics. So this is not the parameter, so we're looking at samples, and instead of sigma, we use SD for standard deviation. It turns out, though, that the overall shape, mean, and standard deviation, the distribution of this X bar can be predicted ahead of time, which is crazy to think about, but how? It's the central limit theorem, and we're going to cover that in the next course. Next class, sorry, not next course, next class.